All right, gang, we're going to talk about recursion today. We're going to cover chapter 11 in about 15 minutes. It's not that the idea of recursion isn't important. It's just it's something that I think once you get the idea, you could research how to do it when you really needed it. Because it's a programming technique you don't use very often unless you go on and you take a 4-year computer science degree and they make you write some recursive algorithms. Also, if you're going to do what's known as functional programming rather than procedural or object-oriented programming, I think you wind up doing recursive programming as well. So, what is recursive programming? It's when you write a method or a function that calls itself. Right? Something like this. You write a function. Pretend we're in Python right now. And inside it, you do something. Well, if I was doing Python, why would I do cout, right? And then you call the function again. Now that's the same as an infinite loop, except since it's a function calling itself, it won't run forever, it'll crash the program. The reason being is that each time you go into a method or a function, it allocates a little bit more memory. Right, like in order to hold a copy of this value and a couple other things that have to be allocated every time you go into a method. Now, whenever you leave a method, all that memory is freed. This never leaves a method, right? Goes into it, calls it, goes into it, calls it, goes into it, calls it, and each time it steps into it, it allocates more memory. Since it never leaves this function, right, there's no way out of it, then it never frees it, runs out of memory. Yeah, heck, maybe I'll type that in, right? Just to demonstrate that I'm not lying. All right, I don't even remember what lecture we're on. Let's go take a peek. Looks we're on lecture R, OPQ. All right, why not? Lecture R. All right, we're going to write that silly function I just showed you. When it's done with the spinning wheel of death. Well, it seems to be letting me type even when that's going. Okay, so public static void dummy, right? Because it's recursive, dummy recursive. Why am I calling it dummy recursive? Because it never leaves. You have to have a return statement in it so that it can walk back out of where it's been. So we need a variable, right, parameter to take the value that we're going to be passing in. Why don't we print that out, right? System.out.println x. Let's call ourselves again. Dummy recursive x. Or I can make it x plus 1, right? But it's just going to keep calling itself. It doesn't matter. I'm going to make this as simple as possible. The only thing simpler would be if we didn't even accept a parameter. And in this particular case, I don't think it needs a parameter, right? Because we're not doing anything with it except print it out. But I'm just going to leave it there. Yeah, I might make one more change to it. Okay, so let's do it. Dummy recursive 10, right? Yeah, it's giving me a complaint here. The dummy method will recurse infinitely. Yeah, that's true. I wonder if it knows enough to offer a solution, right? NetBeans knows everything. Maybe it can offer a solution. All right, so when it runs, oh, look at that. What kind of error am I getting down here? What kind of build error? Oh, no build error, right? And it just printed out 10 forever, as expected, right? Until it ran out of stack space. I'm scrolling up the call stack here, and we can see that it went in there a whole bunch of times. Well, why don't we show how many times it went in there, right? I'm just going to pass in 1, and then after every time we print it out, we add 1 to it, right? So First time it's going to print 1, second time it's going to print 2, and so on. We'll find out how many times. All right. At some point, it's mixing our error.out, our system.err.out with system.out, and that's why we're getting all this mangled stuff. Really, all it did was print all the numbers. And then it printed the exceptions. It's just that the ERRs went to the screen before some of these things. We can kind of prove that if we wanted to. Okay, so anyways, that function was able to call itself, I'm calling it a function, it's a method, 14,000 plus times. All right, we're going to veer off on the idea of try and catch. What do try and catch do? Try and catch, if there's an exception generated, you can catch it rather than let it kill your program. So you set it up with a simple keyword, try. You may have seen this in other languages. Common. C++ has it. Python has it, except they call it try and except. Okay, so we're going to try that. And if something goes wrong, it's going to jump down into our catch code. And you use this an awful lot when you get into more sophisticated uses of the Java API, like connecting to the internet or reading from files or whatever. All right, so what's the error that it's complaining about? Where's the very top error? First time we start to see it. Well, you know what? If I don't print anything out, then the error is going to jump out right automatically. We're not going to see any other output. So let's see what it does. All right, so at the top of it, we should see our exception. Stack overflow error. Here's what we're going to do. We're going to come over here. You see what I did? I just copied that exception. java.lang.stack overflow error. I could probably just copy this part because java.lang is already imported into our file automatically. Oh, here we go. So what are we going to catch? If it throws a stack overflow error, we're not going to let it crash our program, right? So once this method generates an error, it throws the exception, which causes it to jump to here, and then jump to here, and so we can print out system.out.println method through an exception, right? System.out.println exception caught, right? And let's print out what exception it really was, right? So plus, whoops, I didn't give this a name. I'm just going to call it exception or stack overflow error. I don't know if that's going to work. Stack overflow error E, and we're going to print out. Oh, it did work. Okay. Plus E dot. Come on. Populate my pop-up list. I forget whether it's get string or toString or what. There it is. Get message. Right. It's going to tell us what happened. All right. And then we're going to print out system.out.println. We are done with the try catch, right? So if there was no error, right, if dummy recursive actually returned successfully, it wouldn't jump into the catch. Try just means go ahead and do this. If there is a problem, jump into the catch. If there's no problem, go to the end of the block here. All right, let's run it. Right? And it caught the exception. Method threw an exception. The exception caught was null. All right, now that's slightly disappointing because the exception really wasn't null, right? It was a stack overflow error. I don't know why I'm getting that message, but I'm going to go ahead and print, for now, stack overflow error, which is what it should have printed. I'm not going to spend the time to diagnose that right now. All righty. So now when it runs, what we're going to see, right, it did the loop, and then the loop threw an error. Excuse me, it did the recursive method. The recursive method ran out of memory, so it threw an error. Try catch caught the error. It executed our little print statement there that said, yo, we caught the exception, and then it jumped to the next line, right? And so our program is done. Let's print out our numbers again. All right, right. So print it out. Seems like is that a different number than we were seeing before? Anyways, so it was able to call itself 12,000 times. Now, if we monkeyed with our settings, we could get Java to allocate itself more stack memory, and then it'd be able to call itself more often, right? But really, why would a function need to call itself that many times? And the answer is that there are some legit uses for recursive algorithms. Sorting. If you're going to do something more complex than a bubble sort, you know, or a selection sort, that kind of thing, then quite often they are implemented as recursive algorithms. Now really anything you write as a recursive algorithm can probably be written with a loop, but it probably is going to be a lot more complex if you do it that way than if you do it this way. Now here's our simple example of a recursive algorithm that actually does something good, and normally we would implement it with a loop. Now we're going to implement it with a recursive method. Reason being is that you are so familiar with the idea of like adding up the numbers between 1 and 10 or something like that, that hopefully seeing it written in an alien way, it'll make more sense, right? Okay, so what are we going to do? We're going to write a method. I don't need to put it inside the try catch because this one hopefully is not going to throw an exception. I want it to do this. I is equal to sum recursively, right? I'm just going to call it sum underscore recurse. The numbers between 1 and 10, right? Or up to 10, you know. Now we don't have that method. And then we can print it out, right? System.out.println, you know, sum of 1 to 10, summation equals, end quote, plus I. Right? Well, let's write this recursively. Now, when you write a recursive algorithm, there has to be some return mechanism that stops it, that starts returning out of the chain of calls, right? So if it calls itself 12,000 times, it's inside itself 12,000 different times. It needs to return 12,000 times. So, it needs to return an int, public static int, sum recursively, so sum recurse. How many times? Int how underscore many. So what are we gonna do? When you write a recursive algorithm, there needs to be two cases. Case one, called the base case. I shouldn't use the word case, right, because that makes us think we're going to use switch case. You have to have two things. One is you either have to have the base situation, the base case, right? The base situation is a return statement so that we can start escaping from our, you know, from our list of calls. And the other one, the other situation is the recursive case, the recursive situation, right? I am going to call them case because that's the official nomenclature in computer science. All right, what's the base case? If our counter, we're going to make this just for simplicity's sake. Heck, why don't we pass two numbers in, right? We're going to start counting at 1, and we're going to go up to 10. So we're going to say int start, comma, int stop. Each time we call ourselves, we're going to increment start, just like we were doing up here with x. Right? So, but we need to see if start has exceeded the value of stop, right? Because if it has, we're done. we can bail out, right? Because once start has exceeded stop, by the way, I'm going to be incrementing the start, parameter. So it's going to go from 1 to 2 to 3 to 4. And when it finally exceeds 10, it's time to stop. And what I mean by stop, it needs to issue a return so that we can start working our way out of the chain. So int, no, what are we doing there? We need to check. If start is greater than stop, we need to return. We are done. That's the base case. We need to return the sum. Well, do we have a sum variable yet? No, we don't. Int sum is equal to 0. Else, we can add 1 to start plus plus. Tell you what, why don't we set the sum equal to start? All right, now I'm getting a little bit annoyed here, because if we're starting at 1, then we don't want to actually call our recursion at 2, so on. So let's see if we can do this. Sum plus equals sum underscore recurse start plus plus comma stop, right? Add 1 to start and then call ourselves again. I am going to move that up here. Right, add 1 to start and then call ourselves again. And whenever we get a return value from that, then return there. Once we're done with that recursive case, we can return the sum. We can actually stick our recursive case here, right? Not liking that, I'm going to stick the return sum here. Now just to see that it's working, I'm going to print these values out. System.out.println, right? We're just going to print start plus a space, right, plus a stop, plus maybe the sum. Just so that we can watch those numbers increase, get an idea of how it's going. And down here, all right, I'm not going to even call dummy recursive. We've seen that illustrated enough. I'm going to remove these comments. All right, run it. All right, it counted from 1 to 10, right? However, sum never increased. Watch that. All right, I took a peek rather than struggle with it. I'm ashamed that I didn't get it right on the first try. This example shows it counting down rather than counting up. I'm cool with that. It's going to take just minor changes. Here's the base case. Once n is less than 1, we're going to stop counting, right? And so this is going to go from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then we we return, our sum, which is stored in n. I see what's going on there, though, is instead, maybe I've got it fixed. Let's try it once more time. Okay. We shouldn't have initialized sum to 0. Let's just start with that. No, we're just going to do it. Right, okay. So int, the high number, what they're calling n. Why not just run with n, right? Okay, and so if n is no longer greater than 0, right? Or no longer greater than 1, we're going to return n. Else, we're going to return n plus our recursive call -1. right? N plus sum of recursive call n minus 1. So this is a base case. Why don't we put our print statement here saying that we're calling ourselves? I wish I'd saved that other one, right? So we're going to print out n. How about this? How about this? Let's print it out at the top of the loop. Right, system.out.println n equals end quote plus n, right? Okay. Then we can watch it run. Might just put it in debug mode, and then I think we're going to be done with this. All right, I got an error here. Oh, that's because when I invoke the function, I'm still passing in 2 numbers. Now I'm passing down 1. So I just fixed that. Here's my function. Hope it works. Right? And so the first time we entered it, n was equal to 10. Then it called itself, and n was equal to 9, and then n was equal to 8, and then n was equal to 7, and 6, and 5, and 4, and 3, and 2, and 1. And then it started returning. So what did it return? Maybe we could break this out just a little bit. Right? System.out.println base case return, right? Plus n. And I think that if we do this, n plus equals, and then we do return n here, I think that's going to work. And after that returns, we're going to, this is the recursive case. Let's give it another shot. Yep, it worked. Okay. So we called it. The first time we get into it, n is 10. It runs down here. It calls itself again with n minus 1, so n is now 9. And so here n is 9, right? And then 8, and 7, and 6, and 5, and 4, and 3, and 2, and 1, until n is finally no longer greater than 1. And so it returns 0 because nothing has changed n yet. So here, n, it returns 0, which gets added to n. And then that value is returned back to the recursive call. So it's working its way underneath, in the opposite order, because, the last time it was called, n was equal to 0, so it starts returning out of the chain of calls, out of the stack of calls. And so the first time it returned a 1, and then after returning a 2, it up here, then we have a 3, and then after returning a 3, 3 plus 3 was 6, and then after returning a 4, right? And we could write this out just a little bit more complex, right? Let's call this int I is equal to sum recurse n minus 1, just so we can print that out, right? And then we'll say sim plus equals I, right? Or excuse me, n plus equals y. And so let's write out what we got, system.out.println got return value, end quote, plus I, right? Now, let's run it one more time. And hopefully this is clear enough. Do read the chapter about it. It's an important concept. I'm not going to give you quizzes on it, but just because I said I'm not going to give you quizzes on it, maybe on the exam I'll say, what is recursion? And you type in when a method or function calls itself. All right, so the recursive case returned a 1. It got a return value of 1, right there, and then it called itself with n minus 1, right? And so it got a return value of, or it returned a 3, and then it got that 3 and it added it to itself, and so it returned a 6. It got that value as a receive, and so on, and it works its way up until we have gotten our answer. Hope that makes sense. Now with all my print statements and stuff like that, it looks more complex. And so if I was going to undo all these print statements so that it looked back like it did before, then we would just say n plus equals the sum of the recursion minus 1, return n. Right. We could even stick the word return right there. All right. Hope that's clear. That's enough lecture on this chapter as far as I'm concerned.
All right, guys, I wanted to work on this a little bit more, the idea of recursion. I really do want you to read the chapter. I never assign a quiz over it, but kind of wish I did, but I do want you to at least read the PowerPoint, gang. Going to talk one more thing about it. I want to write one more recursive algorithm, and I'm going to get it right on the first shot. Let's take bets on that. So what this one's going to do is it's going to search an array. Now, how do you search an array normally? You just start at the beginning and you go to the end with a loop, right? And when you find it, you break out of the loop and ta-da, you found it. Anything you can do with a loop, you might be able to do with recursion, even though it seems a lot more complicated. And you ask yourself why you would want to do it. There are a class of problems where recursion actually is a good idea. And as I mentioned, there's a style of programming where recursion is the approved way of doing things, because in that style of programming, you are trying to reduce the state variables, kind of fewer state variables. And so since a loop has a state variable, anyways, I don't totally get that, so I'm not going to talk too much about it. But what's this one going to do? We're going to search an array. That's all we're going to do. We're going to search an array, find a specific value. So let's declare our array. Yeah, why not do it? Hey, what's this warning up here? What's that? Why is that gone? Oh, I messed something up. That should have said int I equals sum underscore recursion parentheses 10. Right. That's what was there before. Accidentally deleted that. What's this little warning here? Oh, yeah, infinite recursion, right. We knew that. I'm not going to worry about that anymore. Okay, so let's make an array. Fill it with some numbers, right? 6, 4, 8, 6, 1, right? And here's what we want our data to look like, our method to look like. Int found at, the position of it is equal to, I'm going to search the array, and I want to search it for a target, right? I'm looking for the first occurrence of 8, and that's the array that I want to search, and I want to start at index 0. I want to allow myself the ability to specify which index we're starting at, because like if we kept going after we found the first 6, we might want to call it again and find the second one, right? Not really planning on doing that, but it'd be a simple loop to do that. Alrighty, so to make this a little bit clearer, let's not hard code this 8. Let's call that the target. Int target equals 8. Int start equals 0. That was supposed to be an 8, type of 0. All right. And then I can say, search the array for the target starting at that. Or I could even can't call it something complex, or really obvious, like start index. All right, let's write that method. Well, once we get our result, we're going to want to print out the results. I'm going to choose printf. So target %d found at %index %d in %s backslash end quote comma the target value, where it was found at,
and the array itself. So arrays dot toString. I sense a problem. When I typed in dot, it didn't pop up a list of members of the class. That means I'm going to have to add an import up at the top, or I'll let NetBeans do it. ToString, and please print out my array. Right? There we go. All right, we got to get our import added. It's just going to be java.util.arrays or java.util.asterisk. Scroll up here and change that to java.util.asterisk, even though I'm not planning on adding anything else to this particular lecture after this. All right, so there we go. This is what we need to do. We need to write that. It's going to be a recursive algorithm. It needs to be static because we're calling it from a static context. It needs to return an int, which is going to be the index where it was found, or -1 if not found. Right? Search arrays, the name of the method. It needs a variable to accept the target. Parameter variable there. It needs an array. And it needs that start index, right? Alrighty, so if our start index equals the length of the array, then we're done. We've searched all the way to the end, right? Like if you write a for loop for x equals 1 all the way up to 10, once it reaches 10, you're done, right? So that's going to be our first base case. If the start index, oh, let's call it the whole word, right? Even though it's going to scroll off the screen a little bit. There we go. So if the starting index, or the current position is what, what we could call it, I'm going to leave it with starting index. So if the starting index, earlier I called it start index, let's stick with that. So if the start index, where we currently are, is equal to the length of the array, then it's time to bail out. -1. Target not found in the array. All right, so that's the first possibility, but we've ruled out that we're at the end of the array. That's a very important thing to rule out, because otherwise we might try to access something past, n-1, where n is the length of the array, and we get, an exception and blow up. So I can't imagine writing recursive algorithms that depend upon exception handling, but you can do that. All right, so if we have found it, right? If array at our current position, I'm really thinking about renaming start index current position. So if the array at that is equal to our target, then great news, we found it. So return our start index. Really hating that, I'm going to call it current position. Current position, right? I'm just going to copy and paste that, or I could have used refactor to do this, right? Not going to take too long to make those changes. Alrighty, otherwise we need to call ourselves again incrementing the starting position by 1. Right. So return search array. We're still looking for the same target. We're still using the same array, but we want to search the next position, right? So current position +1. That ought to do it. Talk a big game, let's see if it works. And so the target 8 was indeed found at index position 2, 0, 1, 2. Cool deal. Now let's search for something that doesn't exist in the array. Our new target is 9. There are no 9s in the array. Run it. And it was found at index -1. In other words, it was not found. So you could write an if statement, right? If found at equals -1, then print, was not found, else print where it was found.
You know, so if found at equals -1, or just make it less than 0, that bit us the last time, right? Because binary search will return a negative value and not just -1. All right, so if it's less than that, we're going to print out system.out printf or println, meaning it was not found, right? All right, so it searched it, it didn't find it. Now this value 6 occurs several times. Let's search the array for 6 and print out every index at which it occurs. What are we going to do? We're going to say, we're going to set found at equal to some value, right, that indicates that it's okay to enter this loop. Although we could use a do loop, couldn't we? Maybe we could try using a do loop. Let's get all fancy and use a do loop. Okay, so here's what we're going to do. Our new target is 6. Right? Our starting index is 0 still. What are we going to do? We're going to search the array using those values. I'm just going to copy that line. All right, and if, we could just make it a while true loop, why not? Those are my favorite. So while true, right? And so if found at is less than 0, we never found it, right? Let's break. Else, let's print it out and go to the next one. So, else, do that. Just our print message. And increment our start index, right? So whatever position we found it at is 0, we're going to set it equal to found at plus 1. Actually, we could, yeah, right, found at plus 1, because if it finds a 6 here at position 0, we want to start our search at 1. All right. So, the starting index is now equal to the found at position where we found it plus 1. And then keep looping. And do we want to keep track of how many we found? Good, right? Int how many equals 0. Each time we find one, let's add 1 to that value, right? How many plus plus? System.out.printf parentheses found %d, that's going to be how many of the target %d. That's about enough. We don't need to print the array. End quote, comma, right? How many did we find? How many? That fills in that placeholder. And our target was target, right? And let's add some print message up here to distinguish this output from what was going on earlier. So system.out.println, searching the array for target, or for all occurrences, end quote, \n, end quote, plus quote, of target, end quote, plus the target, right? Let's move that down right below where we set the target, right? So I'm going to cut that and put it above the while. And now I think I'm done with that, right? No, this is a stupid place to put it. This right here needs to be after the while loop. Why do I say that? Because we don't want to print how many we found until we're done with our while loop, in my opinion. All right, so that's our current code underneath the other one. Let's see if it works. All right, so we're looking for 6. We found it at position 0. We found it at position 3, and we found 2 of them. I guess I didn't need that backslash in there. That kind of makes it look lame. Replace that. Just that. And let's set the target equal to something that's not in the array, like 7. All right. So we're searching the array for all occurrences of target 7. We found none in there, right? So we never found any. Okay, so you have 2 examples of recursion now. 3 if we count the infinite recursion. Our examples were getting the summation recursively. For this to work, you'd better start at 1 unless you want to get the recursion like... Nope, never mind. This is the end value, right? We want the recursion of 10, excuse me, the summation of 10, then n will be 10 the first time. And each time we call the recursive algorithm, we subtract 1 from it. Now I'm going to make a minor change, because if you return here, you don't need an else here, right? So this makes it a little bit cleaner, maybe. Right? And I could even delete the braces if I wanted. All right, that's looking pretty clean. Oh, hope it still is comprehensible. That matches more closely this version, right? Where we have 1 base case, and then we found the value, so return index. Second base case, and if neither one of those work, this is the recursive case. Call ourselves again, incrementing current position. All right, I think that's enough. I'll scroll down slowly through the rest of the code in case you need it. And here's the old code, the prior code. Do remember try catches. That's actually the most important part of this lecture, so of course we will get that again next lecture.